All right, let's take a look at these buffer calculations. We know that buffer systems contain a weak acid and its conjugate base. We showed the derivation of the Henderson-Hasselbalch equation, which gives us a very quick way to figure out the pH of a buffer solution by looking at the pH equals the pKa plus the log of the concentration of the base. So that's going to be your conjugate base, usually coming from a salt containing that conjugate base, and then over the concentration of the weak acid. And again, these terms are just coming from rearrangement of the Ka equation. So we're asked to find the pH of the buffer before and after adding 10 milliliters of 1 molar sodium hydroxide. So we are given the Ka, so we can find the pKa, so that's the negative log of 1.8 times 10 to the negative fourth. So that's 3.74. We'll keep 2 decimal places since that was a 2 significant figure Ka, and the log of, so the base, so again, if we've got formic acid and sodium formate, the formate ion is going to be our conjugate base. So we're going to take this concentration of that salt, again the sodium came in as a part of that compound, but it's just a spectator really, so we don't care about that being there. And then we've got the formic acid concentration right there. So if we do 0.7 divided by 0.5 and do the log of that plus the 3.74, that gives us a pH of the buffer to start with is 3.89. So we know that the more base we have compared to acid in this ratio here, the more elevated this pH will be for the buffer above our pKa. Again, if these two were equal concentrations, the pKa would equal the pH. So that's something to note. And likewise, if we had this reversed, if there was more acid than base, then this would come out to be a pH less than. So again, if you're trying to figure out how to adjust the concentrations of these two things, if you were designing a buffer, you would factor that in getting a pH different from your pKa. Okay, so that's for before. If I add 10 milliliters, so here's where we have to be careful of volume changes, because I had 0.500 liters, and I'm adding 10 milliliters. So we also have some dilution occurring, so we have to watch that with our concentrations that we're adding. So for the sodium hydroxide, again, I'm really just concerned about the hydroxide. It's going to be reacting with the acid. So the formic acid, we'll just abbreviate it as HA, and it's going to be producing water, and then this anion is going to be released. So I want to look at, well, what are my starting amounts of moles? Again, because we've got changing volumes, we want to be careful about not just working with concentrations, because we're going to miscalculate our concentrations that get plugged into here. So the base we have, I'm going to do my calculation down here. We've got 0.0100, so that's liters of base, and it's 1 molar sodium hydroxide, so that's 1 mole per liter. So this is 0.0100 moles of hydroxide, sodium hydroxide, but hydroxide that was added. So I have 0.0100 moles of this. The acid concentration, so I have that, but I want to convert that to moles. So the acid concentration was 0.5. Again, I'm told I have 0.50 liters, so I want to make sure I just factor all that in. So I have 0.50, that's moles per liter times the volume of the conjugate, or sorry, times the volume of the buffer. So 0.5 times 0.5, should be able to do that in my head. 0.25 moles, and I'm going to keep 2 significant figures because that is all that my concentration of acid allows. So 0.25 moles. So all of this hydroxide is able to be reacted. So I'm going to subtract off, again, this is just stoichiometry, and I have some amount of water formed. I'm more concerned with this amount of A minus that's formed, and A minus times, let's see here, so we had the 0.70 times 0.5, just to figure out the moles of that. So this is the 0.35 moles. That's how many moles of that we started with, and again, that's our base, right, the 0.7 molar, and that was a part of the 0.5 liters of buffer we had. So we're going to be adding to that the 0.0100 moles, and so I end up with 0.36 moles of A minus. The OH is all reacted, which is what the buffer does, and then I end up with Or if I could read my handwriting, that would be great. This is 0.25, so 0.24 moles. Now, this is my HA. So I'm going to plug these numbers back into here. If I want to find out what the new pH is, go right back into the same equation. Although we have to adjust for the fact that we have now in volume, we've got 0.5 liters plus the 10 milliliters that we added, which is 0.010 liters. So 0.51 liters. Okay. Now, technically, since this is in the same volume and we're dividing the concentrations, by one another, this will kind of cancel out if we forgot to do this. But let's see what that gives us. So again, my pH is going to equal the pKa plus, so my concentration of my base is going to be 0.36 divided by 0.51, so that's 0.706 molar, and the moles of acid, that's 0.47 molar. Log 3.74. All right, so we end up with a pH of 3.92, and that should make sense. We're adding a base, we see the pH go up. It doesn't go up as much as if the buffer components weren't there, but the pH does go up. And so again, if I were given an acid to do this calculation with, if an acid was being added, the acid that's added is going to react with the conjugate base that's present, and so then this is what you'd have. And again, so you'd have to factor in how much acid, how much of the conjugate base got used up, and then how much of the acid, the weak acid, was formed, and then these numbers again would get plugged into your Henderson-Hasselbalch equation. So there are some buffer calculations for you.